everybody. So we're talking about the distributive property, and the distributive property is covered in the Algebra Nation book. It's section 1, topic 3. That way, if you need some more examples or something like that, you can always go back to your Algebra Nation book. So our essential question was, how does the distributive property apply to polynomials? Use the distributive property before when it just has to do with integers, and in the bell work from this week, you guys have also been using it to multiply an integer factor times a polynomial factor. That's what you do anytime you saw a problem like 3 times 2x plus 4. Anytime you multiplied and got 6x plus 12, for example, you were taking this monomial, just happens to be a purely numerical monomial, there's no variables, but it's a monomial nonetheless, and you multiplied it by this binomial inside the parentheses. So you've already been doing this. Our objective is for you to now be able to use the distributive property to multiply two polynomials. Specifically algebraic polynomials, something with variables in it. All right, so the distributive property applies specifically to multiplication. And it says that when you want to multiply two expressions, so that your two factors are expressions, not just integers, you multiply every part of one expression by every part of the other. So I want to use integers right now to see why this is okay. So traditionally, if I was left, or if I had something like 3 times the quantity 10 minus 7, what I would do, according to the order of operations, is I would do 10 minus 7 first, and I get 3. Then I would multiply that by 3, and I would get 9, right? Well, the distributive property says that I can take this 3 and I can multiply it by each one of those terms inside the parentheses before I subtract. So if I do 3 times 10 and 3 minus 3 times 7, I get 30 minus 21, and sure enough, 30 minus 21 is 9. So those two things are equal, meaning I can get my answer two different ways. I can follow the order of operations, or I can distribute. Now, it's kind of silly to distribute with integers when it's really kind of easier just to add what's in the parentheses. But when you're talking about expressions with variables, sometimes you can't add. So let's look at another example where each expression has two terms in it. So regular PEMDAS tells me to do 3 plus 4 is 7, and 6 plus 5 is 11. So 7 times 11 is 77. Okay? But if the distributive property works here, and I do it correctly, I should be able to end up with 77 by multiplying each thing inside the left-hand term, 3 plus 4, times each piece of the right-hand factor, 6 plus 5. So this is where it gets a little tough because you have to keep track of your numbers. So I'm going to do 3 times 6, and then I'm going to do 3 times 5. Now I'm going to do 4 times 6, and I'm going to do 4 times 5. Okay, now this is a really long drawn out way to do this, and we would never do it this way with just purely integers. So 3 times 6 is 18, 3 times 5 is 15, 4 times 6 is 24, and 4 times 5 is 20. So now I have to add all this up. I mean, this is a real pain. I have 8 plus 5 is 13, plus 4 is 17. So I've got 10, 20, 30, 40, 50, 60, 70. Look at that, 77. So this over here in red, that's just really a silly way to do that with integers. But let's see what happens when one of your factors is algebraic and you have a variable in one or both of the factors. We can't do PEMDAS and subtract inside the parentheses. We have to keep those symbols in place because we don't know what X stands for. But what I do know I can do is I can use the order of operations to take this factor out here, 4x, and multiply it by each term inside of the parentheses. Same as you all have been doing with the bell work, where there was just a number on the outside of the parentheses or a fraction. So I'm going to do first 4x times 3x. And I'm writing it out here so that you can see where all of the numbers come from. So 4 times 3 gives me 12, and then I have x times x. So x times x is x to the second power, or x squared. And then I'm going to add to that 4x times negative 8. So 4 times negative 8 is negative 32, and then I still have that x there that's being multiplied. So now what I have is 12x squared minus 32x. Okay, so now we have one a little bit more complicated. This is a monomial, negative 5x multiplied by a trinomial, 3x squared plus 4x minus 9. So I'm going to take my negative 5x, I'm going to multiply it by 3x squared. I'm going to multiply it by positive 4x, and I'm going to multiply it by negative 9. So let's do negative 5x first times 3x squared, and I'm going to write out x squared. X squared is x times x. Then I'm going to do negative 5x times 4x, so I've got plus negative 5x times 4x, and then I'm going to do plus negative 5x times 9. Okay, so when I do negative 5 times 3, I get negative 15, and I have x times x times x, so that's 3 x's, so x cubed. Next, I have a negative 5 times 4, that's negative 20, and I have x times x, so x squared. And then last, I have negative 5 times positive 9, that gives me negative 45. And then I have this little solitary x right there, so that just gets attached onto the end. So this expression here, negative 15x cubed minus 20x squared minus 45x, that's another way to write this original expression up there at the top. Okay, so then what happens when you have more than one term in both of the factors? This is where it gets a little messy, like it did in the first problem that we did. So I want to make sure that I multiply every term in this left-hand factor by every term in the right-hand factor. And that's tough. You have to keep track of what you're doing. So I'm going to take 3x times negative 4x. I'm going to take 3x times positive 7. I'm going to do negative 6 times negative 4x. And then I'm going to do negative 6 times positive 7. Okay, so when I do 3x times negative 4x, 3 times negative 4 is negative 12, and then x times x is x squared. I'll move on to my next term. I have 3 times positive 7 is positive 21, and then I have this x left over. I've got negative 6 times negative 4. That's positive 24, and then I have an x. And then I have negative 6 times positive 7. That's going to be plus a negative 42. So now what I want to do is I want to take my expression that I just wrote and just clean it up a little bit. In algebra, we don't want anything that's unnecessary, and we don't want any like duplicated terms. We don't want any. If there's an x squared in the equation, we only want one x squared. We don't want a bunch of terms that are x squared. If there's, an x cubed term, we only want one x cubed term. We don't want 3 or 4 of them. So I'm going to take anything that is similar, or what we call like terms, and I'm going to combine those. So the first thing, I'm just going to work left to right through the equation. Notice this equation right now is written in standard form for the most part. The term with the highest degree is first, a second degree term, I have 2 first degree terms, and then I have a 0 degree term because there's no variable here at all. So I've got negative 12x squared, and there are no other x squared terms, so that one just comes down all by itself. Now here I see I have an x term and an x term, so I'm going to add those two things together. I have 21 x's here and 24 x's there, so 21 plus 24 is 25x. And then the last thing I have is this plus negative 42. Well, this is a little messy having plus negative, so I'm going to get rid of the plus sign. I'm just going to make that minus 42. So what I've done here is I've written an expression using the distributive property that is it is equal to the expression that we started with, but now I've gotten rid of all of the parentheses and everything. There's a lot of keeping track of numbers that go on to make sure that you've multiplied everything. But I have a little shortcut way that I want you guys to know about too, because that might be a way that you like to do this. Okay, so I want to take that same problem and I want to look at the area model. What is the area model? How can it help you multiply polynomials? Well, if you looked at that last problem, it's kind of a pain to keep track of all of those numbers and to make sure that you're multiplying everything by everything that you're supposed to. So the area model is just really a way to organize your information. Some people love it, some people don't. It's up to you whether you use it. I do want you to know that it exists and how it works, because you may be faced with a question where somebody has filled in part of the area model, and maybe you need to identify their mistake, or maybe you need to fill in a missing step or something. So I want you to know that it exists, but if it's not your favorite way to do this, then stick with what works for you. Okay, so first thing I'm going to do is take my first factor, and it doesn't matter if you put this on the top or on the side, but each piece of this factor needs to go on the same side of the square. So I'm going to put 3x minus 6 on the top, and then I'm going to do this negative 4x plus 7 on the side. Okay, so now what I want to do is I want to take my negative 4x and my 3x and multiply them together. So 3 times negative 4 is negative 12, and x times x is x squared. Next, I want to take negative 4x and negative 6. Negative 6 times negative 4 is positive 24, and then I still have that x there. Now I want to take 7 and 3x and do 21x in this box. And then down here, I'm going to do 7 times negative 6. That's negative 42. Okay, so now with these area model squares, if you have your polynomials written across the top and down the side in standard form, this one is written in standard form. This has an invisible degree of 1. This has a degree of 0. So this is written in standard form. Negative 4x. Once again, an invisible degree of 1. And then 7 has a degree of 0. So also written in standard form. If your factors are written across the top and down the side in standard form, there's a fun trick that you can use to remember what you need to add. So I'm going to take a line diagonally across this. Okay? Anything that this line crosses gets added together. So I'm going to add together 21x and 24x, and I get 45x. Now, there's nothing that goes with the x squared, so I'm going to do 12x squared. And then there's nothing else to add to the 42, so I'm going to do minus 42. So if you notice, this was the same expression, the same equivalent expression that we got in the previous slide doing just regular distribution. Okay, so remember, this distributive property only works with multiplication. You have to multiply every term inside the left side factor with every term inside the right side factor. And the area model is a terrific way to keep track of all of your numbers when your factors have more than one term. And also remember that if you need more examples or some more information, maybe you need somebody to explain it a little differently, in Algebra Nation, this is Section 1, Topic 3. Hope you learn lots!